Okay, in the previous lecture, we defined what are graphs, then subgraphs, and some related notions like edges, adjacency, and things like that. Right. Now, let us look at a few more definitions before we go into applying these things. We have, let's say, a graph G, we denote by V comma E. And we have a graph H with the vertex at V dash and edge at E dash. We say that the graph G and H are isomorphic. They are said to be isomorphic. And we write, of course, G isomorphic to H in this way. If one can find a bijection between the vertices, right? So V and V dash, such that UV is an edge if and only if phi of U, phi of V is an edge. Okay. So what we are saying is that if there is an edge preserving bijection, right? So the edges are preserved in both ways, right? So you have the graph G, then you have a bijection from the vertex set of the graph to the vertex set of the graph H. And we are saying that whenever you have, let's say, vertices U and V in the graph G, they form an edge, right? UV is an edge. Then phi of U, the images, right? Phi of U, phi of V is an edge in the graph H. And if UV is not an edge, then phi of U, phi of V is not an edge. And vice versa, right? So if phi of U, phi of V is an edge, then we want UV to be an edge. And if there is no edge between phi U and phi V, then there is no edge between U and V in the graph G. So if this such a bijection is there, then we say the graphs are isomorphic. And this map phi, which does this job, right, shows the isomorphism. That they are isomorphic is called the isomorphism. So there could be several isomorphisms, but one of such maps is an isomorphism. So if you have an isomorphism, then the graphs are isomorphic. Here is an example, right? You have the graph, complete graph. I have, represented it in this way, right? 1, 2, 3, and 4. And I have a very different representation of the same graph, but with vertex, of course, the vertex set is different, so I cannot say the same. But it's again a complete graph on 4 vertices, where I labeled it with A, B, C, and D, right? So A, B, C, D. But now I have represented in a very different manner. But these two graphs, even though they look different, are essentially the same, right? In the sense that they are isomorphic. So what is the isomorphism between these two graphs? Well, here is one, right? I can say that 1 goes to A, right? 1 is mapped to A by the isomorphism. Phi of 1 is equal to A. Then 2 goes to C, right? 1 goes to A. One goes to A, then 2 goes to C, 3 goes to D, and 4 goes to B, right? This is an isomorphism. And one can verify it is an isomorphism by looking at whenever there is an edge, 1, 2 is an edge, so therefore correspondingly what I want, AC must be an edge. But now the graph is complete, so therefore all possible edges are there. It's a trivial isomorphism. So we don't have to discuss it further. Now, here is another example of an isomorphism. So I have the graph G here, right? 1, 2, 3, 4, and 5. And then I have this graph, let's say 1, 3, 5, 2, 4, and 1, right? So I have this graph G bar. So these two graphs are isomorphic. Okay. Now these two graphs are isomorphic because one can see that one can see that there is an isomorphism. What is isomorphism? You can just see, like if you take one, let's say maybe I need to use a different right? One, then let's say that one is mapped to one itself. Then 2, right? So 1, 2 and 1, 5 are edges. So therefore, I want to make sure that wherever these guys are going, that should be also edges, right? So therefore, I want 2 to be going to let's say 3 or 4, right? One of these I have to do. So then once I map that, I can see that, okay, 2 is adjacent to 3. So therefore, if 2 is going to 3, then whatever that is, it should be mapped to 3 is adjacent to 5 here. So therefore, whatever is that adjacent to here, right, 4 must be mapped to this. And similarly, you can find out the rest. So this will give you an isomorphism, and one can verify that it is indeed isomorphism. Now, let us define something else. Let us take a graph. Let's take a graph G. Okay, so take a graph G, and then whenever there is an edge, I will make a new graph on the same vertex set. Whenever there is an edge in the graph G, I will say that there is no that edge is not present in the graph G bar. Now, if there is no edge between two vertices in the graph G, I will say there is an edge in the graph G bar. Okay. So I take the graph G, every non-edge of G becomes an edge, and every edge becomes a non-edge. Right? Such a graph is called complement of the graph G. Right? So here I have the graph G and its complement. And in this particular case, it happens that the graph is isomorphic to its complement. It's not always the case. You can just see very easily that if you take some other example, like let's say you take this graph, right? Let's say 1, 2, and 3. Then what is the complement of this? Like I have 1, 2, and 3. Now 1, 2 is an edge, so therefore there is no edge between 1, 2 in the complement. 1, 3 is not an edge, so therefore 1, 3 will be an edge. 2, 3 is an edge, so therefore 2, 3 will not be an edge. So I get this graph, right? So these graphs are not isomorphic, you can see. Okay, now the number of edges incident with a vertex of a graph is called the degree of the graph, degree of the vertex. Okay? So the degree of a vertex is the number of edges which is incident with that. Now, this is a very important notion. We will use it quite frequently. And especially in combinatorics, we use it for counting things and studying several properties of objects. So now let us look at some examples, right? So you have this graph drawn here, and in this graph, I have the vertex y, let's say, right? If I pick y. Now the vertex y has edges, right? 3 edges which is incident with. You can see from the picture. So that is the advantage of using the picture. If I had the set theory description, you have to count how many occurrences of y, right, as one of the endpoints. Now here it's very clear. So I have 3 edges. So these 3 edges are incident with y. So therefore the degree of y is 3. Right? Similarly, if you take the vertex x, it has 5 edges incident with it. So therefore its degree is 5. Similarly, the vertex Z has only one edge. Its degree is 1. Now, if you look at all the vertices, look at their degrees, right? You can collect them together. Now, if you look at the smallest value among these, right, numbers, right? So the degrees of each vertex, look at the smallest value. That smallest value is called the minimum degree of the graph because the vertices with the smallest degree, its degree is the minimum degree in the graph G. So I denote it by small delta of G, the minimum degree of the graph. Small delta of G is the minimum degree. Now, if you look at the largest degree, right, maximum over all the degrees, then it is called the maximum degree of the graph and it is denoted by capital delta. Okay. So these two are deltas, small delta and capital delta. Again, these notations we will use very often, so you should try to remember that. Now, let us take a graph and suppose all its vertices have the same degree. Okay. So then we say the graph to be regular graph. So if you saw some example of regular graph before, for example, this graph was a regular graph, right? You had every vertex had degree exactly 2, right? 2 edges. And this similarly the complement is the same. And we had the complete graph, right, on 4 vertices. Every vertex of this graph has degree exactly 3. So therefore that is also a regular graph. So regular graphs are important because it has more nice properties. So one can study those properties. And therefore that comes quite frequently. Now, we now study the first theorem of graph theory. Okay, so what is the first theorem of graph theory? It's called the first theorem of graph theory usually. It says that the number of vertices of odd degree in a graph is always even. Okay. So you cannot have a graph where you have odd number of odd degree vertices. And why is this? The proof is immediate because if you sum over all the degrees, it is always twice the number of edges. Okay. Now, suppose you have this, right? Suppose you have sum of all the degrees equal to twice number of edges, then the theorem is immediately clear. Why? Because if you have the graph where there are odd number of odd degree vertices, then remaining vertices, if there are, will all have even degrees, right? So now let us look at the sum of the degrees. Then you have even times something plus odd times odd, right? So therefore I have an even number plus an odd number, which is an odd number. But odd number cannot be twice the number of edges, which is an integer. So therefore, if I have this theorem, then I know that the number of vertices of odd degree must be always even. Now, how do you prove this theorem, right? That the summation of the degrees is twice the number of edges. Well, it should be very clear if you think about it for a few seconds. But let me explain. If you take the graph and sum over all the degrees, so what happens? So every vertex you are going to count the number of edges incident with it. Now, if you look at in terms of the vertices, this is what we are doing. But now let us look at what happens with the edges. Now, an edge contributes to the degree of the vertices which are incident with it, right? So if I take an edge, it has exactly 2 vertices incident with it, the endpoints of the edge E, right? So look at the endpoints of the edge E. Now E contributes to the sum, right? The sum of the degree sum. We are looking at the degree sum. And in this degree sum, the contribution of an edge is basically 2 because it contributes 1 to one of the endpoints and another one to the other endpoint. So both endpoints contributes 1 or this edge is counted by both of the endpoints exactly once, right? So 2 times we are counting the edge. So therefore, we are counting all the edges exactly 2 times each. So therefore, I have 2 times the number of edges. Right. So the total degree is twice the number of edges, which is always an even number, and therefore you cannot have odd number of odd degree vertices. Now, let us take a graph G, and then what we do is to let us look at this example first. Let us say that I start from a vertex, let's say 1. Okay? So I start from 1, then I go to 2 by an edge. After that, I proceed to the vertex 3. Then I decide, okay, I will go back to 2. Now I go again to 3. Then I go to 5. And then I decide to stop. Okay. So basically, I have taken a walk, right? So supposing that this is a road network, I can think of this as a walk. From the point 1, I go to 2 by the road, then 2 to 3. Then for whatever reason, I decided to walk back to 3 to 2 again. Then I go back to 3 again once again, and then go to 5, and then okay, I decide okay, enough of walking today, and I stop. So therefore, this is a this is called a walk. Okay. So a walk is basically a sequence of vertices, or sometimes it is defined as sequence of vertices and edges, such that alternate or consecutive, not alternate, consecutive vertices is always an edge, right? So if you have V1, V2, V3 to Vk, right, some labels of the vertices which form a walk in the graph, if V1 to V2 is an edge, V2 to V3 is an edge, V3, V4 is an edge, etc. Vk minus 1, Vk is an edge. Now these vertices need not be distinct, right? You can repeat them. For example, as I said, I can go from V1 to V2, then I can go to V1 again, then go to V2, then go to V3, again come back to V2 and V1, right? So all these things are possible. So a sequence, starting with let's say X, then which is V1, V2, etc. Vk, is said to be an XY walk where Vk is Y, right? If Vi plus 1 is an edge for every I in 1 to K, 1 less than K. Now, if it happens that the starting point is the same as the ending point, then the walk is said to be a closed walk. So for example, if I start with 1, right, I go to 3, 2, 3, then go back to 2 and then back to 1. Then that is a closed walk in the graph. So here are some examples. 5 for 5, 3 to 1, 2, 3, right? In this graph, right? 5, then 5, 4, then 5, right? 3, then 2, then 1, then 2, and 3, right? It's a 5 to 3 walk, 5, 3 walk. Similarly, if you look, but on the other hand, if you look at 5, 4, 3, 1, 2, 3, this is not a walk, right? Because 5, 4, 3 is okay. But then 3 to 1 is not an edge, right? 3, 1 is not an edge. So I cannot say that this is a walk because 3, 1 edge is not present. Now, suppose you have a walk in which, I don't allow the repetition of edges. Then we say it is a trail. Okay. So a walk in which no edge appears more than once is called a trail. So trails are walks where you are not allowed to repeat the edges, but you are allowed to repeat the vertices. For example, if you want to look at the same graph, I can define the following trail, right? I go from 1 to, or maybe let's say that I start from, 3, 4, 4, 5, 5, 3, 3, 2. Okay. That is a trail because 3 to 4 is an edge, 4 to 5 is an edge, 5 to 3 is an edge, 3 to 2 is also an edge. And I don't repeat any edge, but I repeat the vertex 3. That is okay, right? Therefore, we have a trail. So the trails can repeat vertices, not edges. Now, if I don't allow repetition of any vertex also, then a walk is called a path. So a path is a graph of the form, let's say P equal to V comma E, where V is the set V0, V1 to Vk, and E is the set of edges, right? Is the edges V0, V1, V1, V2, V2, V3, etc., Vk minus 1, Vk. There are no other edges. The precise set of edges is given here, V0, V1, V1, V2, right? So the consecutive edges form, consecutive edges are in an edge relation, right? So if then the graph is called a path graph, if precisely these edges are present. Now on the other hand, if I am talking about a graph and then looking at a subgraph which is isomorphic to a path, then that a graph can have other edges, but the path that we are looking at is just a subgraph of the graph. So if a subgraph of a graph is isomorphic to a path graph, then we say it's a path in the graph G. Another way to define a path in the graph G is to say that it is basically a walk where I don't allow the repetition of any vertex. So then you can clearly see that the consecutive vertices form an edge, right? Edges, and therefore, since there is no repetition of vertices, there cannot be a repetition of edges. And then we will see that you have precisely the set of edges as we want in the path. So I get a path as a subgraph. Now, suppose it happens that you have a path, right? Let's say we want to like let's say 1 to 5, right? In this example, and then suppose I also add one more edge, starting from the endpoint of the path, right, to the beginning of the path. So if I add the additional edge, right, then we say it's a cycle. So V0, V1, V2, etc., Vk minus 1. If you have a graph, then I add the edge Vk minus 1 to V0, then I will get a cycle. So a path together with one more edge connecting the endpoint forms a cycle. So here is an example of a cycle, right? So we have 1, 2, 3, 4, 5, and then 5 to 1. Again, cycles also can be subgraphs. If there is a subgraph isomorphic to a cycle graph, then it's basically a cycle in the graph. Now, if you want to define in terms of walks, you can see that basically cycle is like a walk where like where we don't allow repetition of vertices except for the starting vertex can be repeated exactly once, right? So I can come back to the vertex. So it's basically a walk where we don't repeat any vertex except for the starting vertex and ending vertex can be the same. Now, for all these walks, paths, trails, etc., you can define, the measure called the length of the walk. So the length of the walk, trail or path are basically the number of edges in this. Okay, so we usually denote the number of edges to talk about the let's say distance or length. So so here we have a path of length 3, right? You have 4 vertices, and then you have 3 edges, right? So you have a path of length 3. Then you have an example of a cycle of length 4. You have 4 vertices, which forms a cycle. So the length is again the number, so therefore the length of the cycle is 4. Length of the path here is 3. Now here is a very interesting theorem. What I want you to do is to think of a proof. I have given a hint here. So what you want to show is that every graph G contains a path of length minimum degree of G. Okay, so every graph contains a path of length, it's equal to its minimum degree. Okay. Now, why is this true? So here is a hint. I say that, okay, let us start with a path of the largest length, maximum length in the graph G. Okay, so P is the largest path in the graph G. So we can denote P by some UV path, where U is the one of the endpoints and B is the other endpoint of the path. And since it is a path, I know that all these edges are present in the graph, right? So you have a UV path, which is the largest path in the graph. Now, can we use this information to say that every graph G, right, contains a path of length equal to minimum degree? So here is the proof. If you think about it for some time, you will get it. But you can stop and watch for think about it for a few minutes. But then I continue. So what I do is that I look at the UV path, which is the longest path in the graph. Now, since this is the maximum length path, let us look at the vertex U, right? Now, if the minimum degree of the graph G is 1, since there is at least one edge in this graph, you know that there is a path of length 1, right? So if minimum degree is 1, then I am done, right? So I have an edge, therefore I have a path of length 1. Now, suppose it is not the case, right? If the minimum degree is more than 1, then the vertex U, which is the starting point of the path P, right, will have at least some additional neighbors, right? Delta neighbors are there. Only one of them is present here. All the remaining delta minus 1 neighbors must be present in the graph, right? So let us look at the remaining neighbors of U. Right? Where can the neighbors of U go? Right? I claim that there cannot be a neighbor of U outside this path P. Right? So this is the path P, and then I say that all its neighbors must be in the path P itself. Now, why is this? Right? So if I look at the vertex U, suppose it has a neighbor outside this path P. If there is a neighbor outside the path P, then let me start from this neighbor, wherever it is, right? So let us say that this is X, right? So X to U I go, then U to V I go, right? Because the vertex X is not part of the path P, this is a path of longer length, right? I can go from X to U first, and then I can go from U to V taking the path P. So I have a longer path. But we started with the assumption that P is the maximum length path. So this tells us that all the neighbors of U must be in the path P itself. Right? So all the delta neighbors of U are in the path P, right? Including the neighbor in the path itself. So therefore, every neighbor of U must be in the path P. Now, the degree of the vertex is right? The minimum degree of the vertex is delta. So U has at least U has at least small delta of the many neighbors, right? So now what does it say? It says that the path we are looking at, right? UV path, that path contains at least delta vertices which are the neighbors of you, right? So apart from you have a delta more vertices in this path. So if the path has at least delta vertices present, then the length of the path must be at least delta, right? Because you have, apart from you have delta more vertices. So delta plus 1 vertices must be there in the path. There could be more, but there is at least small delta plus 1 vertices in the path. So therefore, its length must be at least delta of g. So this is why every graph must contain a path of length minimum degree of g. Now, using the same idea, we can prove that if minimum degree is at least 2, then the graph has a cycle of length at least small delta of p plus 1, right? So if a graph has minimum degree at least 2, then it definitely has a cycle, right? And then it says that the cycle has a length at least small delta plus 1. I mean, there is such a cycle. There could be smaller cycles, but you have at least a cycle whose length is minimum degree plus 1. So the proof is essentially the same. If I look at the maximum length path in the graph, right? So P, then as we mentioned, all the neighbors of U must be in P itself. Now, since there is at least delta neighbors, right, for P, if you look at the farthest neighbor of U, right? So look at the farthest neighbor of U in the path, right? All the neighbors are in the path, so look at the farthest neighbor. So this neighbor, since all the neighbors are happening between U and this vertex, you know that there is at least delta plus 1 vertices, right? At least delta of g plus 1 vertices here. There could be more, right? So now I have this path from U to P, I mean U to this vertex. But then, of course, because this vertex is a neighbor of U, I can go back to U from this vertex. So if I look at this path of whatever length is greater than or equal to delta plus 1, that plus this edge defines a cycle whose length, of course, is at least delta plus 1, right? Because delta plus 1 vertices here, we need at least delta edges, and then together with this edge, it will be at least small delta of g plus 1. So with the same idea, we have proved two theorems now, right? First theorem was that if you have a graph G, then it has at least a path of length minimum degree of G. And then if the minimum degree is at least 2, there is a cycle, and the cycle has length greater than or equal to delta G plus 1. Okay. Now let me define what is called the adjacency matrix of a graph G. So this is a way to represent the graph, because whenever we use computers and all, right, you need to represent the graphs in some other way. But of course, there are other uses for the adjacency matrix. We will see some of the uses soon. So what is the adjacency matrix? So we have the graph G with vertex at, let's say, V1 to Vn, right? The adjacency matrix of G is defined by the matrix A is defined as Aij of the order n cross n, right? It's a square matrix where the entry Aij is equal to 1 if Vi Vj is an edge. And if there is no edge between Vi and Vj, right, the vertices of the graph, then the entry is 0. Right? So this is very simple definition. So let us look at an example. So you have this graph here, 1 to 2, 3 and 2, 4 are the edges. Then I define the adjacency matrix like this, right? I write it like this. So I have this matrix with the following entries. 1, 2, 3, 4 are the corresponding vertices, the labels of the rows and columns. And what do I say? So Ij is an entry, right? If and only if Vij is an edge. So since 1 to 2 is an edge, I have this entry. Similarly, this entry, because again 2 to 1 and 1 to 2, right? Similarly, 2, 3 is an edge, so therefore this, and 2, 4 is an edge, therefore this one, right? Similarly, 4, 2, right? And 3, 2, right? So these are the non-zero entries, and then remaining entries are all 0, right? So therefore, I have the adjacency matrix. Now, an immediate theorem is that if you have the adjacency matrix of a graph is given, right? Let's say it is A. Then if you look at the kth power of this matrix, right? So look at the matrix A and look at the kth power. Now, the power means that you are taking a product of the matrix with itself. Because it's a square matrix, I can multiply it many times. So I take A raised to k, which is the kth power of the square matrix A. Now I look at the ijth entry of this matrix, which is a matrix. So I look at the ijth entry of this kth power. The claim is that the value in this position in the matrix A raised to k is the number of walks of length k from Vi to Vj in the graph G. Okay. So the ijth entry is the number of walks of length k from Vi to Vj. Now, this is fairly easy to prove. I want you to think about this and try to prove it yourself, but we can discuss it. So if you want, you stop and then try to find a proof yourself. Now here is the proof. So we use induction on the value of k. Okay. So the base case is k is equal to 1, right? Because I start with the adjacency matrix, and the base case is clear because ijth entry is defined to be 1, right, in the adjacency matrix if Vi Vj is an edge in the graph, right? So there is an edge, then it's equal to 1, otherwise it is 0. So therefore the base case is clear, right? The non-zero entries are precisely when there is an edge, so therefore there is a path and there is precisely one, right? There is an edge, only one edge. Now, now because of this, we can now use induction hypothesis. Right? Induction hypothesis is that the result holds for any value k which is strictly less than n. Then we do it for n. So look at the nth power of a. What is the nth power of a, right? So I look at a raised to n and just look at the ijth entry. That is only entry I need. So the ijth entry of a raised to n is basically, right, a raised to n is a into a raised to n minus 1, right? So look at that, a into a raised to n minus 1 of I comma j. Now, by the definition of matrix products, what is the product of matrices? Product of matrices, a and a raised to n minus 1, right, a and b, is basically summation, let's say m equal to 1 to the order, right, of the size of the matrix, whatever is the number of rows or columns, aim into, right, bmj, but in this case b is a raised to n minus 1, so it's basically aim into a raised to n minus 1 mj. Now of course aim says that there is an edge between I to m, right, if the value is non-zero, and then a raised to n minus 1 m comma j by induction is the number of walks of length n minus 1, right, from m to j, right? Now if there is an n minus 1 length path from m to j, and there is a path of length 1 from I to m, then there is a path of length n from I to j, right? So since a raised to n minus 1 of m comma j is precisely the number of paths, number of walks, right? Number of walks, not paths. Number of walks of length n minus 1 from m to j. I can create a path of length n precisely when, right, going through this vertex m, precisely if im is an edge, right? So I'm basically counting with this way, right? So I look at every vertex which has a path of length n minus 1 to the vertex j, and then I see if there is an edge from vertex I to m, direct m, then I can basically make an n length path. So I can add this number. So I just add them together. So all the non-zero entries will sum to the number of walks of length n, and that is the proof. So therefore, we can prove that the ijth entry of the kth power is the number of walks of length k between I and j, right, from I to j. Now, I will stop this with a definition of what we call directed graph. So a directed graph is basically, right, so when we defined the graph earlier, we have said that we are looking at just two elements of it, right? Now in directed graph, we want to say that, okay, the order is important. So I will say that I can have a path from a vertex u to, I have an edge from u to v, but there is no edge from v to a, right? So I can basically, the one way traffic, let's say, right? So from point A to point B, this road is going from A to B, but you cannot take your vehicle from B to A. You're taking this road because it is one direction. So this way, we want to generalize this idea, then we can say directed graph. So directed graph is a pair, let's say V comma A, right? Where V is a set whose elements are called vertices as usual, and A is a set of ordered pairs of vertices, which we call arcs, right? Sometimes it's also called edges, but we can call them as arcs. So what are the, so what is an example? So let us look at the given graph below, right? With the vertex set V, 1, 2, 3, 4, 5, and the arc set 1, 3, 3, 4, 2, 1, 2, 4, 4, 5, and 5, 4, right? So it says that, right, 1, 2, 1, 3 is an arc, so it means that I can go from 1 to 3, right? It's a directed. So in the graph representation in the as a picture, we will also put an arrow mark to say that the edge starts from 1 and ends at 3. So it's 1 to 3 with the arc direction, right? So similarly, I can have an edge from 3 to 4, 4 to 5, and also I can have 5 to 4 also, right? Because I allow this multiple things, right? Going from 4 to 5 and also from 5 to 4. So therefore, I have this graph, right? Which we call the directed graph. Now, if you look at the directed graph, the degree can be defined as we can count separately the edges which are going out and which are coming in, right? So the number of edges which are coming in is the in degree, and the number of edges which are going out are called the out degree. So out degree is basically the set of all y such that xy is an edge, right? So that is the out degree of x. Similarly, set of all y such that yx is an arc is the in degree of x, right? So usually denoted by d minus and d plus for the out degree. So I think with this we can stop, and we will continue with further topics in the next class.